Hello everybody, welcome to this video. A couple of announcements. The Achieve Chapter 1 Part 2 homework is due Monday at 9 a.m., so this Monday, September 11th. Chapter 2 PowerPoint will be posted over the weekend, probably on Sunday, and we're going to start that in class on Monday, so make sure you have it downloaded or printed before class. And then this video is for students that are in the 11 a.m. session, since we weren't able to meet synchronously on Friday. So if you were in the 9 a.m. session and you attended class, you don't need to watch this video. You're certainly welcome to if you want a refresher or want to review anything. But if you are in the 11 a.m. class, definitely watch this video before class on Monday. So at the end of class on Wednesday, we talked about measurements and determining the number of significant digits in a measurement, and that depends on the instrument precision. So I have another example here where we're reading a meter stick, and if we're trying to find how long this blue line is, we know for sure it is greater than 2 centimeters. It's greater than 2.5. Let me change my color here. It's greater than 2.5, and we know for sure it's greater than 2.7, but it's not quite at 2.8. It's a little bit before 2.8. So we have 3 digits here. The first digit is 2. We know that we're past 2 centimeters. We know that we're past 2.7 centimeters. Both of those digits are certain, and then the last digit we estimate, and that's between 2.7 and 2.8. So we could report this length of 2.76, 2.77, 2.78. Those are all estimated digits for that very last significant digit. And that's as precise as we can get with this meter stick. We wouldn't be able to add an additional decimal place to say like 2.771. That is a limitation of the meter stick, so that's only as precise as we can get. Is 2.76, 2.77, essentially 3 significant digits. So this just reviews that the 2 and the 7 are certain known digits, and then the final digit is estimated, which is uncertain. But all 3 digits in this case are significant. That includes the estimated digit. Okay, so that wraps up significant digits, and we're moving to section 1.7, which is titled Dimensional Analysis. And the goal here is to use units of a measurement as a guide in setting up calculations and converting between different units. So sometimes we need to convert measurements from one set of units to another. Kind of like if you're driving in Canada, they use speed limits in kilometers per hour. In the United States, we use miles per hour, and so you might need to convert between miles per hour and kilometers per hour. You might need to convert from centimeters to inches, pounds to kilograms, quarts to liters, etc. There are a bunch of different conversions that we could do. So we'll go through an example to explain how to set up these conversions, and then a few examples that you should try on your own. So let's say we're trying to convert 3.8 inches to centimeters. In any case, we start by identifying the starting unit, so that is inches, and we write the value that's provided in that unit as a fraction. So 3.8 inches over 1 is equal to 3.8 inches. And then we look for the target or the ending unit, in this case centimeters, and we use the necessary conversion factors to perform this conversion. Some cases you only need one conversion factor, like 1 inch is 2.54 centimeters, and then you can convert inches to centimeters. In other cases, you need multiple conversions in order to get to your target unit. Okay, so that's steps 1 through 4. Once you have all of that information, then we write the conversion factor as a fraction such that the initial unit, so inches, is on the opposite side of the fraction. So in this case, we put inches in the bottom when we do the conversion. So that way, when we carry out the equation or the calculation, we cancel out that initial unit, which is shown in step 6. So we multiply the starting fraction and the conversion factor, and we cancel out all units as necessary. So any unit that appears on the top or the numerator of a fraction and the bottom or the denominator of a fraction can cancel out. So we perform this calculation, 3.8 over 1 times 2.54 over 1. That final answer is in centimeter units. So we have our final answer. So the next slide, we're going to skip this question here. So the next slide has some learning checks converting the following measurements into a different unit. I encourage you to pause the video here and try working through these, and then we'll talk through them together. Or I'll go through both of these. You might pause after going through the first one. But it will definitely be more beneficial if you work through these independently as opposed to just watching me work through them. But for the first question, we have centimeters. We have 100.0 centimeters. We're converting to inches. So we follow the steps, write our initial measurement as a fraction, and then multiply by the conversion factor. We know that 1 inch from the previous example in the table is equal to 2.54 centimeters. So we will use that conversion, but now we want to put centimeters at the bottom so that we can cancel out the centimeter unit because we're aiming to end in inches. So we've canceled out centimeters. We do 100.0 divided by 2.54. We get 39.37 inches. We start with 4 significant figures. In our conversion factor, we have 1 inch equals 2.54 centimeters. These are one of the conversion factors that we talked about at the end of class previously, where we say that these are an exact number and unlimited significant figures. So when we do conversions like this, our end significant figure amount is limited by whichever measurement we are provided. So we have 4 sig figs in the starting measurement, we have 4 sig figs in the ending measurement. For the next one, just looking at the number, I'll write here we have 2 sig figs, so we know to have 2 sig figs in our answer. We are converting inches to micrometers. We know from the 2 previous examples how to convert from inches to centimeters. Once we are in centimeters, we can then convert to meters. We know from previous notes that there's 100 centimeters in a meter. Once we're in meters, we can convert to micrometers, where there's 10 to the negative 6 meters in a micrometer. So let's write that out. We have 4.5 inches provided to us. Now you could Google how many micrometers are in an inch and use that one conversion, and you'd have your answer. But I will write out the longer equation, the longer calculation, using what we know from our notes. So we have 4.5 inches. Let's first convert to centimeters. So I'll just cancel out units as we go along. Done with inches. Now we'll go to meters. Canceled out centimeters. And then now we'll go to micrometers, where 1 micrometer is 10 to the negative 6 meters. So now we've canceled out all units except micrometers. So when you punch this into your calculator, you can keep each as a fraction, or you can do one step at a time, where we'll do 4.5 times 2.54, and then that answer divided by 100, and then that answer divided by 10 to the negative 6. And you should get in your calculator 114,299.9 micrometers. But now we need to convert to two significant figures. So you can write that as 110,000, or in science we communicate with scientific notation, so that would be 1.1 times 10. Now let's trace to find what the exponent would be. So we go 1, 2, 3, 4, 5 units over. So that would be 1.1 times 10 to the 5th micrometers. The next two slides in the 9 a.m. class, I provided the answers, so I'll do that here, and then after the recording, or you could even pause here and try working through it. And then if you have any questions about them, feel free to send an email or ask if we have time during class or in an office hour. So 9.6 milliliters is 9.6 times 10 to the 6 nanoliters. 22.4 centimeters cubed is 0.0237 quart. .25 miles per hour is 0.011 kilometers per second. Now in this one, as you're working through it, notice that you need to convert miles to kilometers and then hours to seconds. So there are multiple conversions here. And then 2.7 times 10 to the negative 3 years is 8.5 times 10 to the 4th seconds. The next one we'll do together. So we have 3.89 centimeters cubed to inches cubed. Looking at the provided number, we have 3 sig figs, so we'll use that in our answer. Now if we have 3.89 and we want to convert to inches cubed, we know we can use 1 inch is 2.54 centimeters. But since we are given in centimeters cubed and we want to end in inches cubed, we actually need to raise this whole fraction to the power of 3. So I'm going to just rewrite this 3.89 centimeters cubed over 1 times, now if we apply the cube to 1, that's still 1, so we have 1 inch cubed, and then we need to cube 2.54, and that is 16.38764, and then we cube units, centimeters cubed. So now you can do 3.89 divided by 16.38764, and you should get that this is 0.2374 inches cubed. See, we cancel out centimeters cubed. And then we need to reduce to 3 sig figs, so we have 0.237 inches cubed as a final answer. All right, 2 more examples here. So you have the work on your slides. I told the 9 a.m. class this was not intentional, so you can kind of see how this question is worked out. But we'll go through it anyway. So the average speed of helium is at 25 degrees Celsius is 1,255 meters per second. And we're asked to convert this to miles per hour. So if we start with 1,255 meters over 1 second, we need to do 2 conversions. One is converting meters to miles, and the other is converting seconds to hours. In this example, they start with converting meters to miles. So we'll do that, where there is, for every 1 mile, you have 1,609.3 meters. So now we can cancel out meters, and if we were to end the equation here, the number we would get is the speed of helium in miles per second. But we want to convert to miles per hour, so we do another conversion here where there are 3,600 seconds in 1 hour. And then we get our final answer, can cancel out seconds. We have miles per hour left over, and we get 2,807. One more example here. How many minutes does it take light from the sun to reach the Earth, given that the distance from the sun is 93 million miles, and the speed of light is 3 times 10 to the 8th meters per second? Okay, so we have the speed of light, and we're trying to find how long it takes light to reach the Earth, and we know how far the sun is from the Earth. So our end unit should be minutes. We're looking for how many minutes it takes, and we'll have to use the information provided to get there. Because the distance from the sun to the Earth is given in miles and the speed of light is in meters per second, first thing we'll do is convert miles to meters so that we know how far away the Earth is from the sun in meters, which aligns with the speed of light that's provided here. The other thing that you could do is convert the speed of light to miles per second, and you would be able to calculate the final answer as well. So there are different ways to complete these calculations. But let's go ahead and convert 93 million miles. to meters, so we have 1,609.3 meters for every 1 mile. So we can cancel out miles. Now we know how far the sun is from the earth in meters. So if that's how far the sun is, and the speed of light is 3 times 10 to the 8th meters per second, now we can say if for every 1 second, the speed of light, or light will travel 3.00 times 10 to the 8th meters. Now we're canceling out meters units, in which that's good because we're trying to get to a time unit. So now we're only in seconds. That's the units that we're working with here. So we converted the distance from miles to meters, and then now we're seeing how long it takes for light to travel that distance. So we use the speed of light. If we ended it here, we would find how long it takes light to travel that distance in seconds. But we want, or the question asks for the answer in minutes. So now we convert seconds to minutes. So for every 1 minute, we have 60 seconds. And that gives us our final answer of 8.3 minutes. So it takes light 8.3 minutes to reach the earth from the sun. These next 2 questions have to do with temperature, and we actually need to go back to when we learned about converting between temperature units to complete these questions. So keep in mind, now this was covered in an earlier lecture, but temperature in Celsius is equal to 5/9 times the temperature in Fahrenheit minus 32. Temperature in Fahrenheit is 9/5 temperature in Celsius plus 32. And then temperature in Kelvin is temperature in Celsius plus 273.15. For this slide, and this is what I did in the 9 a.m. class, I will explain the process but not actually work out the calculations. If that's something that you would benefit from practicing, you should certainly practice that. If we are calculating, so we're given Celsius and we're converting to Kelvin, we use this third equation. We add 273.15 to 37.0 degrees Celsius. And you would get 310.15. But since we're adding, we have to end at the tenths unit here. So the actual answer with the correct number of sig figs is 310.2 Kelvin. The next one, we're converting Fahrenheit to Celsius. So we use this first equation. Plug in the number for Fahrenheit, solve for Celsius. And with 3 significant figures, if you plug this into your calculator, you should get 37 degrees Celsius. But to keep the 3 significant figures, we write 37.0 degrees Celsius. And then lastly, Fahrenheit to Kelvin requires 2 calculations. We convert Fahrenheit to Celsius first, and then we convert Celsius to Kelvin. And then this answer is 229.26 Kelvin. This next slide, we have the same process, converting calculations. To compare which temperature is the highest, you need to convert all of these to the same temperature scale. So I would probably convert to Celsius, because we have one equation to convert Fahrenheit to Celsius, one equation to convert Kelvin to Celsius. But if you convert all of these to Celsius, you will see that 25 degrees Celsius is the highest. The rest of these are lower. And that brings us to section 1.8. So this is the last section of chapter 1. In the book, there is another section, 1.9, and that's all about temperature, but we've covered that throughout the unit. So in this section, we'll calculate density, volume, or mass when two of the three values are given, and then we'll be able to use density to identify substances. So density is a measure of how much mass something has relative to how much space it takes up. So the calculation or the equation for density is a mass over volume. And then the question here, looking at these two pictures, A and B, picture A and picture B, using these scales, think to yourself which is more dense. So we're comparing capital A and capital B, and then capital C, capital D. So between A and B, both of these substances, these solids, have the same volume. They take up the same amount of space. But A is shown to be heavier since it's lower in the scale. So that means for the same amount of volume, A has more mass, so A is more dense. It has a higher density. Now conversely, comparing C and D, these two substances have the same mass because they're equal to each other on the scale, but C has a larger volume where D has a lower volume. So that indicates that D is more dense. There is more mass in a smaller amount of space. Or this, comparing to C, it's the same mass but in a smaller amount of space. So that makes D more dense. So density is mass over volume. You will often see density as the Greek letter rho, and then mass over volume, capital B for volume. It is calculated from a sample's measured mass and measured volume, and is defined for pure substances at a specified temperature. Density can change at different temperatures. So provided density values are at a specific temperature. Density can be used to identify a sample. So for example, if a sample is found and you're able to determine that the density is 19.3 grams per milliliter, so mass per volume, at 25 degrees Celsius, you can compare that to known densities, and the known density of gold is 19.3 grams per milliliter at 25 degrees Celsius. So you can say this substance is likely gold. Then you could do other tests to determine for sure if it is gold or not for certain. In the past, we talked about intensive and extensive properties, where intensive properties do not vary with the amount of the sample, but extensive properties do. Density is intensive. No matter how much of a sample of gold that you have, the density is always 19.3 grams per milliliter at 25 degrees Celsius. Or for water, doesn't matter how much water you have, its density is always 1 gram per milliliter at room temperature. And for most substances, density decreases when a sample is heated. That's because when a sample is heated, typically the volume of that sample will increase, but you have the same amount of mass. So if you're increasing volume but keeping mass the same, the density will decrease. Here's a list of a bunch of different densities of different substances, different solids and liquids in units of grams per centimeter cubed. Grams per centimeter cubed and grams per milliliter are common density units, but we'll see others as well. We went through this question in the 9 a.m. class, so we can go through it here. Thinking about mass and volume, which object has the greatest density? So we have 4 different possibilities. All of them are in units of gram per milliliter. So let's compare what each of these densities would look like. So rho equals, for simplicity, I'm going to leave out units, but for A, rho is 1 over 1, which is 1. For B, rho is 2 over 2, which equals 1 gram per milliliter. For C, rho, which is density, is equal to 1 over 2, which is 1/2 grams per milliliter. And then in D, density equals 2 over 1, which is equal to 2 grams per milliliter. So all 4 of these samples have densities, and the highest density is option D, where we have 2 over 1. Grams per milliliter. The precision of density in calculations is dependent on the precision of the mass measurement, and the precision of the volume measurement. So if you measure an object's mass to be 4.26364 grams, that has 6 sig figs, and the volume to be 4.59 milliliters, which has 3 sig figs, then you report density with 3 sig figs. And I believe that's where we ended in class. It might be useful for your homework to look at this page where we can use density as a conversion factor. If you're given the volume of something, you can calculate its mass using its density. Or if you're given the mass of something, you can calculate its volume using its density. I'll end the video here so we're at the same place for both classes. And thanks everybody. I'll see you all in class on Monday.